For my lecture, I'm going to be giving an overview of computer engineering as a degree and as a field. Computer engineering is really just creating useful computing systems. For example, your iPhone, your computer, games that you play, etc. And that is a very complicated task because you have to begin with physics, the fundamental physical laws of our universe, and then you have to build upon layers of abstraction until you get to the useful systems like your iPhone, your computer, whatever, right? And I'm going to be giving an overview of these layers of abstraction that we make to make it possible to make these useful systems. And every single course in your computer engineering degree is going to be dealing with one layer of abstraction within this kind of stack of abstractions that we make to get to these systems. And the first of these abstractions is going to be the abstraction from physics, more specifically electromagnetism, which is governed by Maxwell's four equations, and electric circuits. Electric circuits can be very simple or very complex, but I'm going to be grouping them into one category because they all follow some fundamental laws that I'll be explaining a bit later on. And you probably already have heard of some of these laws like Ohm's law, V is equal to IR, right? KVL, Kirchhoff's voltage law, and KCL, Kirchhoff's current law. And this abstraction is probably the most difficult step to understand in terms of intuition because it's pretty difficult to understand these four equations. Well, first of all, these four equations require you to have a pretty solid understanding of calculus. Just by looking at these symbols, you might recognize some of these symbols, but you probably don't understand everything if you haven't taken university calculus, because you see integrals, you see derivatives, right? But I'm going to be trying to explain some of these equations a bit more intuitively in this lecture to give you kind of an intuitive idea of what each equation says. And going from these equations to these very simple equations relatively is pretty complicated in terms of understanding when you can make this simplification, because in some scenarios you do have to use Maxwell's equations to determine what will happen in the system, because these equations that govern electric circuits cannot apply to every system that involves electromagnetic forces, because obviously circuits are a very specific scenario in which Maxwell's equations are applied. I'm going to be giving you an overview of Maxwell's equations, not something very mathematically rigorous, but just as a taste of what each equation says. So I want to begin with talking about electric fields. Now, if you took virtual physics, you probably have heard of them, but I'm just going to go through them again. Electric fields, think of them as simply arrows in space. Every single infinitesimal point in space has a electric field associated with that point. Electric fields can be thought of as vectors, so they have magnitude and a direction. So if you draw the arrow longer, that means that the electric field is stronger. But there are other representations of how you indicate magnitude of vectors, but we don't need to go through that right now. So every single point has an electric field associated with it. And these electric fields are then influenced by electric charges that exist in space. So if you have a positive charge, then that positive charge is going to influence how electric fields around it are going to behave, right? So the direction and the magnitude of the electric fields will be influenced by this charge. And technically, every single electric field that exists in the universe is going to be influenced by this single positive charge. But as you go farther and farther from this charge, the influence of the charge on electric fields is going to decrease and decrease pretty fast. So if it gets really far, then the effect is essentially zero. Now, around a single positive point charge, the electric fields are going to look like this. they are going to point away from the positive charge. And as you get closer to the electric charge, the electric fields are going to be stronger and stronger. So the electric charge, the electric field at this point is going to be a lot bigger than the electric field at this point, which is still going to point away from the positive charge, but it's going to be a lot smaller. Maybe I would draw it smaller like that. And the same thing goes for negative charges, but the arrows are going to be pointing inwards, so into the electric charge. And the same idea, if you have a point very close to the charge, it's going to be a lot stronger than a point very far from the charge. Equation 1 says that this quantity on the left is equal to this quantity on the right. So this quantity on the left is called electric flux. That's Flux. So flux is defined using an integral, but I'm going to be defining it a bit more intuitively. So just think of it as the number of arrows that are pointing outside of a hollow sphere. So that's not very concrete, but let me just give you an example. So let's say you have a positive proton at the center and you have a hollow sphere around it. So this is not a circle, this is a sphere in 3D space that is hollow. And the really important thing to understand about flux is that you define it for purely mathematical surfaces. So surfaces that you just imagine. They don't actually exist. You're just defining the surface so that you can in turn define flux on that surface. So that being said, since this is a positive charge, you're going to have electric fields on this sphere pointing away from the proton. And since you have arrows pointing outside the sphere, so away from the inside of the sphere to the outside of the sphere, you're going to have a positive flux on the surface. So flux is defined for any surface. So flux isn't a quantity that or some vector that exists in nature. It's literally a quantity that we defined for any surface so that we can kind of understand these laws of nature. So flux, like I said, can be defined on any surface, but for a closed surface, the convention is that flux is defined so that if you have arrows pointing away from the inside of the surface, then that contributes a positive quantity to flux. But if you have an arrow pointing inside, so from the outside of the sphere to the inside of the sphere, then you're going to have that arrow is going to contribute a negative quantity to the flux. So I'm saying inside and outside, but this doesn't really have to only apply to spheres. A closed surface is any surface that has a clear inside and outside. So if you have a hollow cube, right? Then you have a clear inside and outside. So if you have an arrow pointing like this, then this is going to contribute a positive quantity to flux. And if you have an arrow that's pointing into the cube, then you're going to have a negative contribution to the flux. Erase all of that. And the same idea kind of goes for negative charges. If you have a negative charge in the center instead, then you're going to have a negative flux, because you're going to have arrows pointing into the closed surface, in this case, a hollow sphere. And you can kind of see where this is going, right? Because if you have a positive charge, then you have a positive flux. If you have a negative charge, you have a negative flux. So this quantity here, this Q enclosed, is the sum of the charges inside the closed surface. So in our cases, with these two examples, you only have a single charge inside the surface. So in this case, you're going to have Q enclosed is equal to some positive charge that corresponds to whatever value this proton has. And in this case, the Q enclosed is some negative charge. But you can also have cases where you have a proton and an electron inside the sphere. This is a completely valid configuration. So what this equation says, right, is since you have a net neutral charge inside the surface, because Q enclosed is equal to the sum of all of the charges inside the closed surface, then you're gonna have a zero flux on the surface. And this kind of makes sense, right? Since if you look at this point in space, this proton is gonna be making the electric field want to point this way, but this electron this electron is gonna be making this electric field want to point this way. But since this proton is closer to this point, then this has a bigger effect on which way the electric field points. So the electric field is going to be pointing outwards, but not as big as if we didn't have this electron. And the exact opposite thing kind of applies on this point, right? You're going to have an arrow pointing like this because this proton wants to make this electric field point this way, but this electron makes this electric field want to point to the inside. And since this electron is closer to this point, it has a bigger effect. So the arrow is going to be pointing inwards instead. And since you have this arrow pointing this way and this arrow pointing inwards, then this kind of cancels out. And that's why you kind of have that zero flux. And that's basically all this equation says. Equation number 1 just says that the charge inside a closed surface is equal to the flux on the surface. And although they're not exactly equal because you do have this proportionality constant, you don't really have to worry about it too much because it's not fundamental to understanding this relationship. You just have to remember to have this constant added to this equation to kind of make it work. The second equation says that this quantity is equal to 0. And what this quantity is magnetic flux. And magnetic flux is defined exactly the same way as electric flux, except that magnetic flux uses magnetic fields instead of electric fields. So the reason why magnetic flux is equal to 0 for any closed surface in space is because magnets always come in dipoles. So you probably have seen this diagram. You have the North Pole and the South Pole, and magnetic fields come out of the North Pole and into the South Pole. They kind of look like this. And if you construct a closed surface, like let's just say this closed kind of rectangular prism, then the flux on that surface is always going to be 0. And it's pretty easy to see why, right? Because if you look at this point, then you have this magnetic field going out. Same thing with this point. But if you look at this point, you have the magnetic field coming in, and the same thing with this. We have it coming in, right? So these kind of cancel out. And it turns out that this is always the case with any magnetic field line that exits and enters a magnet. So you always have this cancellation. That's why the flux on this rectangular prism is always going to be 0. So equation number 3 and 4 are pretty similar to each other, but they are a bit more complex to understand compared to 1 and 2. So I'm just gonna be writing down equation number 3. Something to note is that this quantity, this funny symbol with a B as a subscript, is magnetic flux. That's just how physicists write magnetic flux. So I'm going to be giving an example to kind of explain this equation. So let's say you have a ring in 3 dimensions. So this is a ring in 3 dimensions. So if you look at it from this angle, this is kind of like your eye, then you see a circle. And let's say you have magnetic fields that are going in this direction through this kind of enclosed area, right? So this is just free space. These fields are going through basically nothing, but it just happens to be that nothing corresponds to the area that is enclosed by this ring or this path, right? So since you have a surface, remember that a surface can be purely mathematical. In this case, it literally is because there is nothing on the surface. Then you can define flux on that surface. So you can define magnetic flux on the surface that is enclosed by this ring. And that is this quantity, this magnetic flux. And this left quantity, so I kind of have to go at this a bit more mathematically, but you have this ring, right? And let's say you have electric fields that are going like this on the ring. So at these points in space, you have the electric fields pointing in this direction as some magnitude. And what this quantity says is that you take these fields and you compare the direction that these arrows are pointing in with the tangent to the circle, right? And you say that tangent has some vector that is going along the tangent. Don't worry about the actual direction and magnitude of the vector for now. So since you have these two vectors, you can take the dot product of the vectors, right? So if you have the magnetic field going like this and the tangent going like this, then you maximize the value of the dot product. Of course, it's limited by the magnitude of the two vectors, but relatively is maximized. And this is what this is. You sum up the dot product of all of these electric fields, and so the dot product of the fields along with the tangential vectors, and you add them up. So if you have an electric field kind of going like, I might have said magnetic field, but these are electric fields. So if you have something like that, then you have the tangent like this, right? Then you have this kind of situation. Then you take the dot product of these two vectors. So it's not going to be just a straight multiplication, it's a dot product. And you add that up for every single field on this circle. And this is what this is, right? You might recognize this as the derivative of the magnetic flux. So what this says is that if you have a closed path and you have a changing magnetic flux on the enclosed area for that closed path, then you're gonna have some of this quantity. It's not exactly electric field, which might be a bit confusing, but it's this quantity that involves electric fields and the path and like the direction that the fields point in relative to the path. But if it makes it simpler, you can just think of it as if there's a change in magnetic flux, then you generate electric field, right? So if you have a wire, so if this ring was a wire instead of just some random ring, then you have magnetic fields going along the wire if you have a changing magnetic flux going through this enclosed surface. And this field, like you can imagine, can push electrons through it, which creates current, which is something that we actually use. You might notice the negative, but don't worry about it too much. That just has to do with the direction of the magnetic fields, or sorry, the magnetic fields, and how that relates to the direction of the electric fields. But don't worry about it too much. It gets a bit more confusing if you kind of get into that, because you then have to define things with the right hand rule and stuff like that. Equation number 4 is essentially the same thing as equation number 3, but you have the magnetic field and the electric field reversed in terms of what they do in the equation. So you have this, which is just the same thing as this left side on equation number 3, but now you have the magnetic field instead. And on the right, you have this, plus this term. So this thing, or these two things, I guess, just think of them as constants. Don't have to worry about them too much. This I'm going to kind of ignore for now. It is important, but I don't think it's too fundamental to understanding what this equation actually says. And this is the electric flux. Right, so if you have the ring again, and you have electric fields going through this enclosed area, then you have the electric flux defined on this enclosed area. Then if you have that electric flux changing with time, then you have some of this quantity being generated, which is magnetic field along the path. Again, it's not necessarily a one-to-one correspondence with just generating this magnetic field. It's generating this weird magnetic field and path dot product quantity. But if it makes it simpler, you can think of it as literally generating a magnetic field along the ring. And again, we do use this equation quite a lot in things like generators, right? So those are the 4 Maxwell's equations. Hopefully you kind of got a glimpse of what each equation says. And yeah, that's kind of my goal. My goal wasn't to kind of fully explain them to you. It's more of just to give you an intuitive sense of what each equation says, so that you can kind of see that it's not too abstract, although it is pretty abstract, but you can kind of reason through them in terms of physical scenarios happening. For electric circuits, I kind of just want to give you a very simple example and just go through it. You probably already have seen this kind of circuit if you took physics in high school, right? You have a battery, in this case it's 9 volts, and you have a resistor. In this case, this is going to be a light bulb that's 3 ohms. So the 3 fundamental things that you learned probably is Ohm's law, which says V is equal to IR in any resistor. Remember that you can't just apply it to any random component. It has to be a resistor. And you also have KVL, which is Kirchhoff's voltage law, which says that if you go along a loop and you add up all of the voltages, then you get 0. And you also have KCL, which says that if you add all the current going through and, going into and going out of a node. That's probably a better way of explaining it. Then you have 0. So kind of explaining these 3 fundamental laws on this circuit. Let's say you want to find the current going through the circuit. So the first thing we need to do is define our voltage drops and voltage rises. So since this is a battery, obviously if you go from this side to this side, you have a voltage rise. And since this is a resistor, if you go from this side to this side, you have a voltage drop. You signify that with a positive going to a negative. Let me just move this out of the way. And since this is a resistor, you can use Ohm's law. So V is equal to IR. In this case, you know that the resistance is 3 ohms. So you can simplify this to 3 times I. And we're going to be applying KVL to the circuit. So let's say you start at this point on this loop and you would go along this, right? You come across this component. So as you pass this component, you have the voltage rise of 9 volts. So that's plus 9 volts. And as you go along, you have this voltage drop of 3I. So we're going to signify voltage drops with negative. So negative 3I. And you come back to this point. And we know that this must equal to 0, right? So you now have I is equal to 9 volts divided by 3. This should really be 3 ohms, so that you get 3 amperes. So we now know that the current is equal to 3 amperes. I'm not going to be going through any more examples because circuits are more just getting used to these 3 equations than really any kind of difficult math. The most difficult math you do with electric circuits is solving very big systems of equations. And you do get to complex math once you do AC, which is alternating current. But even then, these 3 laws kind of apply to the complex space. But I'm not going to get too much into that. And yeah, like electric circuits can get really, really difficult. But as long as you understand these 3 laws very well and you get a lot of practice, you will be fine. And let's move on. And I want to talk about some abstractions that exist within this big category that I defined as electric circuits. So you have these abstractions from this thing to this thing, right? So on this side, you have this very complicated looking circuit, but usually we just want to write this entire circuit as this very simple symbol. And that's because electric circuits make use of these components that are made up of smaller components. And obviously, you don't want to draw this every single time you want to use this component, right? This is called an operational amplifier, and they are used quite a lot in everyday circuits. And you do learn about them in your first year circuits course, probably. And yeah, usually you just want to learn how this operational amplifier component behaves. You don't need to know all of this. You might learn about it, but in practice you won't really remember what the circuit does in depth. You just want to know how this thing behaves, right? You have these, let me get a better color. You have these 3 connections, and you want to know how these connections serve the circuit that is connected to this operational amplifier. Now we get to the next abstraction, which is between electric circuits and electronic circuits. So electric circuits are the things you learned in high school, right? Basic resistors, batteries, wires, and I don't don't think you learn much more in high school, but there's some other components. But in general, they are pretty basic. But electronic circuits are things that you use to build computers. And you have these logic gates. You probably have seen these before. You have the OR gate, right? Which is that if you have 1, 1, then this is 1. The output will be 1 if the two inputs are 1. And if one of the inputs are 1, then the output will also be 1. But if both of the inputs are 0, then the output will be 0. And to make this functionality, it's actually pretty complicated because you can actually make this OR gate using electric circuits, but it does require quite a lot of electric circuit components. But we kind of abstract that to just this one OR gate, right? Because when you are designing computers, you don't want to be thinking about how each resistor and how each battery and how each power source is going to be connected. You just want to be thinking about these logic gates and want to think about how the logic is going to flow with in your design to make the system take some input and spit out some output. I want to give you a bit of an overview of what electronic circuit design is. So to begin with, I want to talk about the basic logic gates, right? You have the OR gate, which essentially says that if you have the two outputs X, Y, and you have the output Z, then Z lights up or is equal to 1 when at least one of X and Y is equal to 1. And you have the AND gate, which says that Z will only be equal to 1 if X and Y are equal to 1. And then you have the NOT gate, which essentially just inverses the input, right? So if X is 0, then Z is 1. If X is 1, Z is 0. And using these three gates, I want to show you how to construct any function. So by function, I mean, let's say you have a box, right? And since computers can only understand binaries, so it's either on or off, either 1 or 0, you need to have every single input as a binary. Let's say you have 3 inputs, X, Y, Z, but as we will see later, it doesn't really matter how many inputs you have. And let's say you have the output O, right? I'm actually going to show you some symbols to represent these logic gates that we use in equations. So the OR gate, we usually use a plus. For an AND gate, we usually just use the multiplication. And for a NOT gate, we usually use this, which is an exclamation mark, or you just have a prime. So like if you have a variable X, that's a binary variable, then adding a prime would mean not X, right? So back to this function. So you get this black box, let's just call it F, but you can really call it anything. And let's say we want to define how this black box behaves. And defining it really just means for some values of X, Y, and Z, I want O, the output, to be some value. So we usually do that using truth tables. So we have X, Y, Z, and O. So let's say we usually draw a line here, right? Like that. This is the input. This is the output. So let's say you have 0, 0, 0. If X and Y and Z are all equal to 0, let's say you want the output to be 1, right? And let's say if you have this combination of inputs, then you also want this to be 1. But if it's any other combination, let's say, like that, you want it to be 0, that, 0, that, 0, that, 0, right? So on. How do we make this function? How do we make a function using logic gates that will create this exact behavior, right? So consider this. O is equal to x prime and y prime and z prime, then this thing will only equal to 1 if x prime and y prime and z prime. So it will only be equal to 1 if x is 0 and y is 0 and z is 0. Right? Which is this exact case. If it's any other combination of x, y, and z, then it will be equal to 0 because we're using ands. Right? And if we want to just add this combination, then you just have to add an OR gate. X prime and y prime and z. Not z prime, just z. Right? So in this case, this will only equal to 1 if not x and not y, but and z. It's not and not z, it's just and z. So this will only be equal to 1 if x is 0, y is 0, and z is 1. And for any other combination, you're going to have 0. Right? Because for any other combination of x, y, and z, this thing will be 0, and this thing will be 0. And 0 or 0 is equal to 1. But even if just one of these combinations equal to 1, then since this is a OR gate, this entire thing is going to equal to 1. And you can actually extend this to however many of these terms as you want, right? If you want the 0, 1, 1 pattern to also return a 1, then you can just add x prime and y and z, right? And if you want more variables, you can just add more variables, x, y, z, w, whatever, right? And this is called the sum of products representation, because you have the sum, right, of products, which are these terms right here. And you also have the product of sums representation, but I don't want to get into that. But it's essentially kind of like the opposite. You can search it up if you want. It's not that difficult to understand if you understand this. If you don't understand this too well, just kind of think about it for a bit. I think a lot of digital circuits, and more specifically this kind of logical design, is mainly just thinking about what happens in different cases and kind of reasoning these different logic gates and how they interact with each other. And to actually build this thing, right, you just have to make the individual gates. So in this case, you have the NOT gates and another NOT gate going into an AND gate. So x, y, z, this is going to be the inputs, right? And you have another AND gate. Just going to draw x, y, z's here. Not, but this is not going to have a NOT gate like that. And this is going to be connected to an OR gate. And this is going to be the output. Usually you want to draw them like this. So you're going to have this X signal coming from just one single source. And the same thing with the Y and the Z. It's kind of messy, but I think you got the idea. So this would be x prime and y prime and z prime, and this would be x prime and y prime and z, and this would be x prime and y prime and z prime plus or x prime and y prime and z, right? Which is exactly what this is. I'm ignoring this thing for now, just assuming that this is just what it is. But if you do want to include this, you can just add another AND gate and just connect it like that, right? And this is mostly what digital circuits classes are usually about, just creating these circuits and creating abstractions, because you can link these things together to create more abstract functions, and you can use those functions to build even bigger functions, and usually these functions will serve some purpose that resembles a computer more than these individual or more smaller circuits can. And on that note, there are abstractions within electronic circuits, as you might expect, because like electric circuits, you can abstract these humongous circuits into one component, right? For example, this is a pretty simple component, but having to draw this entire thing might get tiring if you just want to use what this component does as as a function within a bigger circuit. This is called a multiplexer. If you want to know what it does, you can just Google it. It's not very complicated, and you can probably think about how you can construct this multiplexer using the sum of products representation that I talked about. In fact, it actually does exactly that. If you look at this, right, this is just AND gates, and you have OR gates. So, yeah, the sum of product representation is pretty powerful, because really any component is just a function, where you take some inputs and you define a behavior on what the output should be for these certain patterns of inputs. And really your computer chips are just based on these logic gates, right? Even though these might be very complicated. For example, you see here that this is a multiplexer. Let me use a different color. This is a multiplexer, right? So, and these are other more abstract components. So using these abstract components, you can create even more abstract components like this chip. And that's really how your chip, the chip in your computer really works. It really is just a bunch of logic gates connected together, and the inputs come from your keyboard, comes from other chips. Now, the next abstraction is from electronic circuits to some programming languages. So, usually people don't program using these logic gates, right? They don't program using multiplexers, they don't program using the sum of products representation. They program using actual programming languages. And these programming languages can be things like assembly, C, Python, Java, whatever, right? And usually this abstraction is what makes computers possible, because to make the software that you use every day, it's almost impossible, like humongously impractical to make those softwares using logic gates. You need programming languages that abstract these logic gates, right? Because at the end of the day, programming languages send instructions to your computer to do exactly what it wants it to do. And instructions are inputs, and inputs get fed into this really complicated function that is your computer, and it creates some output, which is exactly what digital circuits do. But you obviously have a much more complicated and much more abstracted out circuit than something like this thing that we talked about. And there's abstraction within programming languages themselves, because as you might know, Python is actually written, or the Python interpreter is written using C, or it might be C++. I think it's actually C++, and C++ is written using more lower level languages like assembly. And assembly itself was written using machine language, right? Or machine code, which is just zeros and ones. And yeah, this is exactly what I just said. You have machine language, just zeros, ones, machine language literally looks like zero, ones, one, yeah, zero, one, one, zero, one, etc. And you have assembly, then C, then C++, then so on. Continuing with abstraction within programming, you have things like compilers and different tools and different softwares that actual programmers use, but they don't really realize or really think about how these softwares work. For example, as a Python developer or a C++ developer, you don't really think about how the interpreter or the compiler is doing what it's doing, right? But somebody did have to write that compiler, usually in a language that is lower level than the language that the compiler compiles. But somebody did have to write that compiler or whatever software that you're using. And there's the concept of abstraction built within programming languages themselves. If you've programmed before, you probably know what I'm talking about because you write functions, right? These functions can be really complicated and but really they serve one purpose. Like for example, a function might calculate the greatest common denominator of two integers. You can name it GCD and it takes in two values, right? It does whatever, but really if you want to use the function, you don't care about how it does it, you just want to use the function itself. So functions allow you to abstract this functionality, this code away from using the function. And in your code you can just write GCD and you can call it, let's say like 13, 14, right? And this will output, in this case, this will just be 1. Continuing with abstractions, we get to the final abstraction. This isn't really considered something that relates to computer engineering in the traditional sense, because usually computer engineering programs end at the programming language. They teach you to write programs, but usually a lot of degrees don't really teach you how to build systems. Systems are just different softwares and different computers that are running. So an example of this would be, well, a lot of companies these days run some kind of digital infrastructure, right? They run websites, they run different databases, different applications. Some companies make this their primary business. Like for example, Google, right? When you search on Google, you have all of that digital infrastructure running in the background to make that search possible. So systems are just different components of that digital infrastructure. So these can be things like servers, databases, gateways, and these different abstract things that and these abstract components are gonna be running software that are written by programming languages. And usually these systems are not very complicated to understand theoretically because, like for example, a database, what does it do? It stores data, right? A server, what it does is that it runs code that you provided to it and it runs it at a specific time. So it's not very complicated. So usually these systems don't get taught in a university program and you learn them by yourself. So to recap a bit more about this abstraction flow map, you have physics, Maxwell's equations, they get abstracted to electric circuits. So resistors, batteries, wires, so on. And you can abstract these to electronic circuits. So these are the logic gates and the different components that you can make with logic gates. And you can abstract this to programming languages, C++, C, Python, different programming languages that you can write software in. And the software can be abstracted one step up to systems, databases, servers, Google, different nodes within Google, different servers within Google that are running software. And this is kind of the flow map that we have in our modern system of running technologies. And computer engineering deals with everywhere from the physics to the programming languages, usually. To my knowledge, there are not too many courses that deal with systems. You can't learn that by yourself, but computer engineering does teach you pretty well about how to make this abstraction from physics to programming languages. And I have this red thing to kind of signify that computer engineering focuses on these two things, electric circuits and electronic circuits, and how to abstract from electric circuits to electronic circuits. Physics, we don't really deal with that too much. That's more like we kind of have an understanding of Maxwell's equations and how you can abstract these equations to electric circuits, but we don't study too much into electromagnetism. That's more of a physics degree thing. And programming, as you can guess, that's more of a CS and SE, software engineering kind of thing. Because although computer engineering students do a lot of programming, computer science and software engineering students focus on that a lot more than computer engineering students do. And with these two representations here, computer science students usually don't deal with physics at all. They might deal with electric circuits, although this is almost optional. As a computer science student, you don't need to understand why electric circuits work the way they do. You just have to understand how electronic circuits behave, how these logic gates behave, and how these can be abstracted to make programming languages, and how you can use programming languages to build software. And software engineering students also do kind of what computer science students do, but they also have to take usually at least one class in physics to kind of understand how Maxwell's equations work and how they can be abstracted to electric circuits, but usually not as much as computer engineering students. And software engineering students don't really deal with this abstraction from electric circuits to electronic circuits. They don't really have to do too much electric circuits. Usually they take one class in it and they focus their time on programming and logic gates. And even computer science and software engineering students don't really deal too much with systems because that's more of a thing you learn on the job. And you don't really need school to teach you these things, right? Because they're not very theory heavy. It's more of just understanding the different tools that exist that can help you build different applications. Yeah, so I hope that you got a pretty good understanding of what computer engineering is all about. And I think I will have office hours. So if you want to ask anything about the program, about my experiences, about the concepts in this lecture, although they weren't too many, it's more just an overview. But if you have questions, feel free to ask at my office hours. The date, I think Benny or Ali might tell you. Yeah, right. Thanks for listening.